Today we want to discuss the first isomorphism theorem. So the first because I think there are isomorphism theorems in other aspects of algebra as well. So it's important to, because there's always a fundamental theorem, right? So you have to say, is it a fundamental theorem of algebra or calculus, stuff like that. All right, so what is the statement? The statement is that now let F, which is a map from, say, G to G prime, be a group homomorphism. So I might, from now on, just use GP for group. And of course, I'm already using hom for homomorphism. From the group G into G prime. Now, let the kernel of F be denoted by, say, just K. Okay? Do people remember what a kernel of F is? What is kernel of F? Can somebody say who hasn't taken abstract algebra courses before?
It's the set of elements that maps to the identity in the target set.
Very good, yeah. So this is the identity, E prime, and there is some subset of the first group where all of them map to the identity, okay? So that's the kernel of F of the, this is. So we know that K, okay, sorry, let me just first finish the statement. So let K be the kernel of F, then the first isomorphism theorem, it states that G over K is isomorphic to the image of F, okay? What is G over K? G over K is the quotient group, is the coset space over here, the coset of G and K, but we know that it's a group because we know that K is a normal subgroup. That was one of the things that you had to prove. Okay, so proof. So what do we know? We know, number one, that K is a normal subgroup. Of G. Therefore, G over K is a quotient group, right? That means that the elements of G over K are all cosets, and we can there's a natural group multiplication structure that we can define on that, with respect to which G over K is a group. Okay. So that we know. What else do we know? We know that the image of F, which is a subset of G prime, is also a group. And it's a subgroup of G prime. Okay, so this is one we know. Other things we know is that elements of G over K are cosets of the form G of K, right? So, and number 4 is that elements of the image of K are of the form F of G, where G belongs to big G. Okay, this is just reminding you some of the salient facts and notations. Any questions about this? All right. So
shouldn't it be image of F instead of image of K?
Yeah, sorry. Thank you. Yeah, sorry. Image of K doesn't make sense. K is not a map. All right, cool. Thank you. Any other questions or comments? Okay, so what does the proof involve? Okay, so to prove this, we need to show that there is a one-to-one mapping. There is a one-to-one mapping between the elements of the left-hand side and the right-hand side. The coset space, the quotient group, right, which is this thing, and the subgroup, which is the image of F, right? That's one thing we have to prove. The other thing we have to prove that the map preserves the group structure. Now, what group are we talking about? It's the group which is the quotient space, or the group right here, right? So if you are able to show both of these things, then we have proved the theorem. Do you agree? All right,
Yeah,
so
makes sense.
yeah. All right, so often I find, and I'm not, and I've been that person myself. I often find that it's hard to kind of figure out, when you're trying to prove mathematical theorem, what is it that we are trying to prove? What constitutes a theorem, right? And while I'm not trying to, this is not a course in abstract algebra, or for me, I am not a mathematician, as you know, but I think that it's good to prove a theorem like this so that we have some flavor of that idea. Okay, so number 1, so let's say number 1A. Let's look at the map which is the map from the image of F to G over K. So essentially, if I have okay, well, these are actually new. So this is a G, and this is suppose K, and this is the image of F, right? Now, when we are thinking of G over K, then what happens, we partition G into these disjoint sets, right? Subsets. So there'll be G1K. This is K is just EK, right? It's identity element of G over K. Then we have G2K, G3K, or So what we are saying is that now what we'll have is that we'll look at the map, which is the map from the elements of image of F to each of these cosets. All right, so what we have to do is that if, say, F of G1, which is the form of the elements in the image of F, say is equal to F of G2, then, so, okay, we need to show that if F of G1 is equal to F of G2, then that implies that the coset that G1 belongs to is the same coset as the one that G2 belongs to, okay? That is, G1 is a coset equivalent to G2.